Hello, everyone. This is Mr. Castrol. Today, our video lesson is about the Earth and the Sun. Here's your brain warm-up. Get your Google Doc ready. The question is, how does the Sun move across the sky? Specifically, what direction and how fast does it go? Write down what you think. The answer is that the Sun rises in the east and sets in the west. It moves in the southern sky at about 15 degrees per hour, which is 1 degree every 4 minutes. To get an idea of what I mean by degree, this is about 1 degree, the width of your pinky, left to right. Put 3 fingers together, that's about 5 degrees. So when we do a fist like this is about 15 degrees. So this is what the Sun does in 4 minutes across the sky. This is what the Sun does in about an hour. The essential question for today is, why are days longer in the summer than they are in the winter? To learn that, we will focus on 5 questions. Where is the Sun in relation to the Earth? What is the Sun? Why is it important? Why is there day and night? And why are there seasons? Vocabulary we'll learn today include rotation, axis, hemisphere, revolution, Polaris, which we also call the North Star, solar angle, summer solstice, winter solstice, vernal or spring equinox, and autumnal or fall equinox. So first of all, where is the Sun? The Sun is 150 million kilometers away from Earth. That's 93 million miles. We call this distance 1 astronomical unit. The Sun is so far from the Earth that it takes 8.3 minutes for light from the Sun to reach it. Notice, so we say that the Sun is 8.3 light minutes away. Notice that it's a unit of distance, not a unit of time. How big is the Sun? Pretty darn big. The Sun is 1,392,000 kilometers in diameter. That's 865,000 miles. If you put a line of Earth's end to end across the Sun, you'd need 109 of them. And if you wanted to fill the Sun with Earth, you'd need 1.3 million. So what is the Sun? It's a star. We call it a G-class star or a yellow dwarf. Stars perform nuclear fusion. In the case of the Sun, it takes 4 smaller hydrogen atoms and squeezes them together to make one bigger helium atom. When it does that, some of the leftover matter is converted into energy. How much energy? Every day, the Sun releases 3.86 times 10 to the 26th watts of energy. That's 26 zeros. Put it in perspective, it's like 1 trillion nuclear bombs going off every second. Why is the Sun important? It's important because it is Earth's main source for energy. The Earth doesn't get all the energy the Sun releases at any given time because the Sun is releasing in all directions and the Earth is on only one point in the sky. Still, every day we receive 1.74 times 10 to the 17th watts of energy from the Sun in the form of light or radiant energy, and then the atmosphere converts that into heat. Besides that, plants perform photosynthesis so they can convert this light energy into chemical energy in the form of food. Then animals will eat the plants. Plants and animals and other living things will die, and eventually their bodies become fossil fuels. Basically, almost every kind of energy you can think of, except for nuclear and geothermal, originate from the Sun. To talk about days and years and seasons, we need to talk about 2 terms and understand the difference between them, rotation and revolution. Rotation is a body's circular motion around its axis. The Earth turns on its axis. We say it rotates. So rotate means to spin. The axis is an imaginary line going through the middle of the Earth from the North Pole to the South Pole, from here to here. Let me show you rotation. So here I have a model of the Earth, okay? And here, the Earth is rotating. You will notice that it has a North Pole, a Northern Hemisphere, and a Southern Hemisphere. If we split the Earth in halves, we call each half a hemisphere. The other word I want you to use is revolution. If rotation means spinning on an axis, revolution means going around, orbiting around something else. For example, the Earth and the other planets revolve around the sun. The moon revolves around the Earth. So once again, I can show you quickly. Imagine my head is the sun. This is the Earth. Here is the Earth revolving around the sun. So revolution is a body's elliptical motion around another body. It's another way to say orbit. Earth and the planets can revolve around the sun and move around the Earth. So here we have examples of rotation and revolution. So here we see the axis of the Earth. Here is the northern hemisphere. And here is the southern hemisphere. And over here we can see the Earth revolving around the sun. What is a day? A day is just the amount of time that the Earth takes to rotate on its axis, once every 24 hours. So how does that become day and night? On any given day, so each rotation day, on any given day, exactly half of the Earth is lit up. That half is experiencing daytime. The half that's not lit up is nighttime. Earth is actually casting a shadow over its back half, so light, sunlight, can't get there. That's the difference between day and night. So you can see it right here. So here I've got the Earth. Here I have the sun. And as you can see, half the Earth is lit up and half the Earth is in darkness. As I rotate, different parts of the Earth light up, and you can see the half that's lit up. As the Earth rotates, different parts of the Earth are lit up. That's how day passes into night. Remember, the sun rises in the east and sets in the west. So, for example, New York, the sun rises in New York before it rises for us. That means that the Earth rotates counterclockwise. So if the amount of time it takes for the Earth to rotate is a day, its revolutionary period, how long it takes to get around the sun, is a year. A year is 365.24 days. Why that extra decimal? Well, you know about leap years. Every year, the Earth goes an extra quarter of a day. It needs a quarter of a day to do a full orbit. That means every 4 years, we need to add an extra day. That's a leap year. Since it's 0.24 instead of 0.25, that means every 100 years, we can skip a leap year. So why are there seasons? Believe it or not, it's not distance. 3 things are going on. 1, the Earth revolves around the sun. 2, the Earth is tilting at a 23-degree angle. And 3rd, the intensity of the light from the sun depends on the angle at which the sunlight hits us. Here's a fun fact. We're actually closer to the sun in January than we are in July. So it's not about the Earth being closer to the sun. It's about the angle at which the light hits the Earth. So the Earth tilts at 23 degrees. So if this is straight up at 0 degrees, this would be how the Earth tilts at about 23 degrees. It tilts to the north. there's actually a star in space called Polaris, which we call the North Star. So when we talk about orienting how we look, we'll always remember that the North Pole is, the axis of the Earth through the North Pole is pointing towards this one star. And the cool thing is if you look at the night sky in the Northern Hemisphere, those one star that actually doesn't move during the night is Polaris. I'll show you, here's a time-lapse photo, and you can see this little star in the middle here. That's Polaris. All the other stars, you'll notice that it looks like they're rotating or revolving around Polaris. Now, they're not really revolving. What's really happening is that the Earth is rotating, and as it's rotating, our view of the other stars changes. But because the axis through the North Pole is pointing right towards Polaris, that's the one star in the sky that never changes its position. Our angle of view is always the same. If you ever want to find Polaris, you just have to look for the Big Dipper, and you can find it right here. And you go to the end of the Big Dipper, these two stars here, the pointer stars, and they will point right to the end of the Little Dipper, and that's Polaris. So since the Earth tilts towards Polaris, it keeps the same tilt as it orbits the sun. It orbits kind of like this. I'll just say this is the sun right here. Okay, and it keeps the tilt. But that means sometimes it tilts towards the sun, North Pole towards the sun. Sometimes it tilts so the South Pole is towards the sun. But it always keeps the same orientation in space. That means different parts of the Earth are tilting towards the sun, just as I showed you. In summer, the northern hemisphere is tilting towards the sun. In winter, the southern hemisphere is tilting towards the sun. So you can see here that in the summer solstice, right here, it looks like more of the northern hemisphere is lit up than the southern hemisphere. That is because it's tilting just a little bit to the north. And the winter solstice is the exact opposite. Now it looks like more of the southern hemisphere is tilted to the sun than the northern hemisphere. That looks like an extra section. Now in the fall equinox, you can see it's actually even. It's 50-50. Same is true for the spring equinox. So we call the points at which one of the poles is leaning most directly towards the sun the solstices. When the northern hemisphere is pointing towards the sun, that's the summer solstice. When the southern hemisphere is pointing towards the sun, that will be the winter solstice. The summer solstice is going to be on June 20th. The winter solstice will be on December 21st. So in the summer solstice, the Earth is leaning so that the northern hemisphere is tilting towards the sun, and the southern hemisphere is tilting away from the sun. Whereas in the winter solstice, the southern hemisphere is tilting towards the sun, and the northern hemisphere is tilting away. And once again, that means more of the whole northern hemisphere is not being lit up, whereas more of the northern hemisphere is lit up in the sun. The equinoxes are the 2 days when you get the exact amount of day and night, no matter which hemisphere you're in. The vernal equinox, which is also called the spring equinox, is March 19th next year. The autumnal equinox or fall equinox, which just happened, it was on September 22nd. So you can see, in this case, the line of the light, what we call the terminator line, falls exactly on the axis. So exactly as much of the northern hemisphere is lit up as the southern hemisphere. So once again, to view the seasons, in the summer solstice, the North Pole is lining up more towards the sun, So more of the northern hemisphere is lit up. In the fall equinox, it's 50-50. In the winter solstice, more of the southern hemisphere is pointing towards the sun. In the spring equinox, we're 50-50 again. One more thing to think about. Since the season depends on which hemisphere is pointing towards the sun, where is Australia pointing during American summer? Think about it for a second. Write it down. You should have figured out that when it's summer here, it's winter in Australia and vice versa. When it's winter here, it's summer in Australia. The seasons are reversed in the southern hemisphere. So why are days longer in the summer? I'm going to show this to you really quick. Watch what happens when I rotate the North Pole. Look at the North Pole as I light it with the sun. So there's the North Pole. It's lit up, and I'm going to rotate. And what you should see is that even as I'm rotating, this is 24 hours, the North Pole is constantly getting light. Now think about the South Pole. I've got the North Pole lit up, but look at the South Pole, although it's actually glowing here because it's a bulb, but you should see that the South Pole is actually on the other side, so it's always in darkness. For the same 24. Now, if I reverse it, now you can see the South Pole is lit up and the North Pole is night for that same 24 hours in the winter. Notice the North Pole is lit all the time and the South Pole not at all. That's the summer. And I reversed the tilt and that was the winter. Okay. And that's why you have longer days in the summer. It's because since you're point tilting towards the sun is lighting you up for more time as well as, okay? It's most evident at the poles. As you get further closer to the equator, it evens out. At the equator, you're always at 12 hours and 12 hours, no matter where, what day it is. Now let's talk about what this has to do with making summer hot. We have to talk about the solar angle. We call the angle at which the light from the sun hits the earth the solar angle. The more direct the solar angle, the greater intensity of the light. It's less spread out, it's more concentrated. Also, as a second effect, it passes through less atmosphere when it's direct. So here's the solar angle for the northern hemisphere at winter. Here's the light, and you can see it's covering a very large area. Right? It's covering all this area. So that all this area is only being covered by 5 light rays. If we do the same thing in summer, we can see those 5 light rays hit a much more concentrated area. And we have a total of 15 light rays over the same area. Okay? So you can kind of see it again if we use a piece of paper. Let me show you here. So you see, when I shine the paper like this, it's hard to see with the camera, that it's a bright concentrated thing. But if I bend it up, you can see it's bright at the bottom and kind of spreads out and gets dimmer as it goes up. Okay. Okay. So here, so the basic idea. So now we've seen the solar angle. Days are hot in summer. Since the northern hemisphere is tilted towards the sun, it gets a more direct solar angle. In the winter, the light from the northern hemisphere is tilted away from the sun, so it gets a less direct solar angle. There's a second effect in that since days are longer in summer, the sun is heating the northern hemisphere for a longer amount of time every day than in winter. So here you see the various solar angles. Notice as you get closer to the equator, here, see that? So you get closer to the equator, once again, that the angle is more direct. That's why it's hotter near the equator than near the poles. And I've got a little diagram. You can see two rays of sunlight. And if you look carefully, you can see this one is summer, north in the summer. And that the ray of light in the northern hemisphere is actually smaller. It covers a smaller area. That's the same size ray light you, but the same size hits a smaller area, so it heats up a ton more. So you're getting more sunlight, directed sunlight in the northern hemisphere than you are in the southern hemisphere. Winter is just the opposite. It's tilted the other way, so now the sunlight covers a greater area in the northern hemisphere. Now, the way it looks to us, it looks like the sun is higher in the sky. So this is where it looks like when the sun's rays are covering a greater area in the winter. It's colder because the light is coming at a much more indirect angle than when it's coming at us in the summer. And that's basically why we have seasons. I hope you enjoyed this today. I sure did. Have a great one.